Hello everyone, and thank you for joining us today for this webinar organized by the European-funded Energy-Oriented Center of Excellence. Today's topic will address the work being achieved by the Erlangen Regional Computing Center team on the A64FX CPU computer, which currently powers the #1 supercomputer in the top 500 list. Among other things, the topics will be the execution cache memory performance model the Erlangen team is using for the A64FX processor. The presentation will also address code optimization strategies as well as performance comparisons. Today's speaker will be Christy Alapet from the Erlangen Regional Computing Center. And as a backup speaker, we'll have Dr. Georg Heiger from the Erlangen Regional Computing Center as well. The webinar structure will be the same one we've used for other EoCoE webinar, which is to say a 45-minute webinar followed by some Q&A session. For those of you who are joining us for the first time, just know that you can use the raise hand or ask question buttons under the participant table of the GoToWebinar software, because as attendees, your mic are muted by default. So you'll have to raise hand or ask a question via the software, which I will then open your mic so you can tell your question. The webinar is being recorded. It will ultimately be available on the EoCoE YouTube channel. And once again, thank you for joining. Christy, I'm giving you the floor. Go ahead.
Yeah, first of all, thanks a lot, Julian, for organizing this webinar, and also the EoCoE project for organizing this webinar. So it's my great delight to present or share our knowledge on the A64FX processor. So 3 months back, actually, we got this opportunity to play around with this A64FX processor. So we had an access to this small supercomputer with A64FX processor, which is situated in Regensburg in Germany. So yeah, in today's talk, I would be giving a broad overview on the streaming kernels and sparse matrix vector multiplication, so mainly memory-bound kernels. And we would look into the performance and analyze the performance and do some performance modeling. So basically, most of this talk is based on a joint paper between University of Erlangen and University of Regensburg in Germany. And yeah, so this paper was accepted for the PNPS workshop, which took place in SC this last week. And yeah, so in this talk, I would be giving more details. So also the current research which we did with the A64FX processor. So it would be based on this, but I would also go in more detail. So I would also compare the performance with the current modern CPUs, like from Intel, also from AMD. And finally, we would also compare it with V100 GPUs. And also, I would give you some takeaway message, what we have to be careful when we are dealing with this A64FX processor. So in June this year, we heard a big news that the supercomputer Fugaku, which is a joint development by RIKEN in Japan and Fujitsu, achieved or crowned the top 500 list. It was not just this top 500 list, but it also took the first position in the HPCG benchmark, the Graph 500, the AI benchmark, and so on. So this arose this was something interesting which we needed to look into. So this Fujitsu supercomputer uses the same A64FX processor, and it could achieve a peak performance of 400 petaflops with LINPACK. So in Regensburg, we had a supercomputer with FX700 system, which uses A64FX processor. And the configuration of this system is that it has 4 NUMA domains. So NUMA domains, it's also called as core memory group. So it's CMG. So the acronym CMG stands for, basically you can think it as a NUMA domain. So this has 4 NUMA domains. And each of these CMGs has 12 cores. And so in total, we have 12 times 4, that is 48 cores per node. And if you concentrate on one CMG, so if you zoom in, we have 12 processors, as I said, and each of these cores or processors clock at 1.8 gigahertz. So this is basically a little bit different compared to Fugaku, because Fugaku can clock at 2.2 gigahertz. So practically, this is the only difference between the Fugaku processor and the FX700, more or less. So it's basically this clock frequency, more or less what is different between Fugaku. And it supports, the processor supports ARM version 8.2, and also it supports the scalable vector extension, the SVE. In fact, I think it's the first CPU to implement the SVE instruction set with ARM. And the maximum vector length is 512 bits. So basically, it can occupy 8 double precision elements in one register. We had access only to GCC compiler. Unfortunately, at the time of the research, we didn't have access to the Fujitsu compiler. So we used the GCC compiler, and with GCC compiler, you could produce this SVE instruction set with ARM version 8.2. So this the flags that I mentioned can be used to produce this instruction set. And if you go down the memory lane, you see the L1 cache is fairly a typical one. So a 64 kilobyte cache, and it's private to each course. What's different when you compare it with other modern CPUs is that the cache line size. So the cache line size is 256 bytes. Normally, nowadays, we have 64 bytes cache, but on this mission, we have 4 times the cache line size. The L2 cache, things get a little more interesting because compared to other modern CPUs, this is the last level cache. And because of it, it's a shared L2 cache that we have, and it's 8 megabytes in size. Okay, so this is also the last level cache. So there is no L3 cache for this system. And when you get into main memory, things get even more interesting because instead of the typical DDR systems that you see on modern CPUs, here we have a HBM module, so a high bandwidth memory module. So each of the CMGs are connected to HBM. So in total, we have 4 HBMs on one node. And each of the HBM can deliver up to 230 gigabytes per second on this FX700 system. So in total, we get almost 1 terabyte per second from the entire node. So this is different when you compare it with modern CPUs, where it gets around 200 to 300 gigabytes per second. So it has a improvement. So it has almost 3 times improvement in main memory bandwidth, at least the theoretical main memory bandwidth. And this is also the reason why we investigated more into memory bound codes, because you see that the main memory module is different. So yeah, that's why we investigated also into this memory bound codes. So when we get a new processor for HPC benchmarking, almost everyone's first benchmark to run is the stream triad to measure the main memory bandwidth. So here in this plot, you see on black lines, the black lines correspond to the stream triad bandwidth on this FX700 system. So on the y-axis, you have the bandwidth, and the x-axis is the number of cores. So you see as the number of cores increase, so from 1 to 12 cores, you see a typical saturation pattern. This is because the stream triad actually saturates the main memory bandwidth of this one CMG, because till 12 cores, we have one CMG, and you see within this one CMG, you saturate the main memory bandwidth. And we used a compact pinning, or it's also called a fill type pinning. And because of this, you see when you increase or when you scale across the CMGs or across the NUMA domains, you see that we have a linear increase in performance. And at the end, you reach, when you have 4 CMG, you reach 4 times 200 gigabytes per second, reaching almost 800 gigabytes per second. So we experimented with the stream triad and also several other benchmarks, but 2 benchmarks had a strikingly different pattern. That was the sum reduction, which basically does, it sums up all the elements in an array, and the SpMV, that is, it does a multiplication of a sparse matrix with a vector. Typically, these benchmarks are also memory bound, but we don't see any memory bandwidth saturation pattern with these 2 benchmarks. So you see that it's linearly scaling without showing any saturation pattern within 1 CMG, for example. So this was interesting. We were interested to see why don't we see this, because on typical other processors you see this, but you don't see this on this FX700. And one thing that we have to note is that the single core bandwidth, if you just concentrate or zoom in to the single core bandwidth, you see that the single core bandwidth of triad and sum, for example, has a difference of almost 5x. So sum or SpMV is a matter of fact 5x lower than the triad bandwidth. This was interesting because then you see that there is a problem at single core level itself. So we have to understand the single core performance to know why this is happening. And in order to understand the single core performance, we used the ECM model, the so-called execution cache memory model. So ECM model is like roofline model, performance model. But normally, roofline model is defined on a complete node or a complete socket. But ECM model can also do a performance modeling at a single core level. So that's the benefit of ECM model. So we have to analyze the single core, so that's why we took the ECM model. So basically, ECM model consists of 3 components. The first one is the in-core component. So basically, in-core component is basically has the runtime contribution for data transfer between L1 and register. It also includes the computation time. So it also takes into factor the computation time. So doing like arithmetic, like floating point arithmetic and stuff like that. But in most cases, this floating point arithmetic and computations done in the in-core part overlaps with the data transfer from L1 to register. So it doesn't play, the computations don't play a big role in the benchmarks that we considered. The second important component is the runtime required to transfer data between memory hierarchies. So it can be the runtime between the caches and between cache and main memory, for example. And the third important component is the overlap hypothesis. Now, if we get all this, we get all these contributions, so different data traffic contribution, and overlap hypothesis determines which of these contributions can actually overlap or not. So sometimes it can happen that these contributions overlap. For example, the data transfer between memory and L2 overlaps with L2 to L1, but in some CPUs, you see that they do not overlap. So it's important to note that for each CPU, this overlap hypothesis differs. And for a single CPU, for a given CPU, there is only one overlap hypothesis. Okay. And yeah, so let's dive into the first important component, the in-core contribution. So we make an assumption to get into this in-core contribution. We assume that the out-of-order scheduling is perfect. This means what we just consider is the ports, which executes these instructions. So basically what we take into account is we take into account how many instructions can be executed by a port in one cycle and how many ports can ports are there to execute these instructions in parallel, for example. So I told you that we assume that out-of-order scheduling is perfect. However, it might not be the case with different CPUs. So on the right, you see a diagram of the port model and the reservation station of FX700. And you see that the reservation station entries are like 20 and 10 entries. So in total, maybe like 80 entries or something. And but you see that if you compare it with the modern CPUs, these entries are pretty low. So if the entries in reservation stations are low, it might indicate that we might have out-of-order scheduling problem, which we will see later. But for now, what's important is the ports. So we see first we have an FLA port, which could do floating point arithmetic and also floating point stores, for example. Then you have a predicate port. Then you have FLB, which is a second port which does this floating point arithmetic. And then you have a couple of integer arithmetic ports. And then we have two ports, EAGA and EAGB, to do loads. And it also does this address calculation and so on. So now, once we have this knowledge about the mission, and if you are given an application, so let's take the stream triad, for example, we can map the instructions of this application to these ports and tell how much cycles it takes to execute this application. So it's basically the contribution for executing this application in L1 cache. So in stream triad, the important kernel is this one, because the rest is the loop mechanics. So if you do sufficient unrolling, this is only the highlighted box is the one which is important. And you see that we have one load instruction, and this goes to the EAGA port, for example. The next load instruction can go in parallel because we have two load ports on this machine. And then we have the fused multiply add, which goes to a FMA port. And then we have a store. But on this architecture, you can't do a load and a store at the same cycle, so you have to wait for one cycle. So in total, we need 2 cycles to execute the stream triad from L1 cache. So the EoCoE contribution is actually 2 cycles, and all of these instructions are working on a vector register. So we have 2 cycles per vector length. Okay, so that's our EoCoE contribution. And to do this, there is a tool called Osaka, which can do this automatically. So it does a static analysis on your assembly code, and it tells you what is the EoCoE contribution. And yeah, here I have a table on the throughput and latency of different instructions. And here you see load has a throughput of 0.5 because you see that we can do 2 instructions at one cycle because we have 2 load ports. So it's 0.5 cycles and so on. So we have different throughputs and different latency. What's different when you compare it with other modern CPUs is that the latency of instructions are pretty high compared to modern CPUs. So for example, if you take Intel or AMD, for example, the latency of FAD is normally in the range of 3 to 5 cycles. However, for this architecture, we have like 9 cycles for FAD, for example. So the latency is pretty high on this machine. So this we have to keep in mind when we do measurements. And I'll show you some examples at in the upcoming slides. And the second important component is the data transfer contribution. So as EoCoE model, we also need here the knowledge about the machine or the hardware. Also, this is the information that from the hardware side. So you see that the main information that we need is basically the data transfer rate between the caches. Like here we see between L2 and L1, we can transfer data at a range of 64 bytes per cycle. while the store from L1 to L2 is at a rate of 32 bytes per cycle. So once we have this knowledge about the mission, so how much data can be transferred at a given cycle for different cache levels and main memory, and now we need the knowledge from the application side, like how much data do we need from L2, or how much data do we need from main memory. So if we take our stream triad example, we see that we need to load the C vector, or the C array, and this for one, if we have it for one vector length, we need 64 bytes, so 8 elements to be transferred per vector length, so 64 bytes per vector length. And then we need to load the B vector, which again has 64 bytes per vector length. And then we have to load A first for write allocate and then store back A. Okay, so if we now combine this mission knowledge, that is the data transfer rate and the volume that we get from the application, we can get into our ECM prediction or ECM contribution. Like we see that we need 3 loads from L2 to L1 at a rate of 64 bytes per cycle. This means we need 3 cycles per vector length to load data from L2 to L1. So to store data, we would need 2 cycles per vector length, and so on. So you can get different contributions. So also the loads from memory to L2, how much cycles it takes, and also stores. So we get these contributions, so the data transfer contribution. So now, once we get this data transfer contribution, we can combine it with the EoCoE contribution, which we saw previously. So we combine it with the EoCoE contribution. And now it's the third component that plays. So now the question is, how do these contributions overlap, whether they overlap or not? So this is an important thing to determine for a new CPU. So it can be that none of these contributions actually overlap, like the one you see on Intel architectures. So the current Intel architectures is something like this. This is not that good because you see that all the components do not overlap, which means you have to sum up all the components, which increases the runtime contribution at the end. However, it can also be that all the contributions overlap, like the one you see on AMD Rome system, for example, or it could be anything in between. So you can have numerous combinations. Okay, so how do we find the correct one, the best one for a given CPU? The solution is to compare the measurement with the prediction. So for the FX700 system, the best hypothesis that works for FX700 system is this one. Here we see that there is an overlap between the stores from register to L1 with the L2, L1 contributions. And also there is an overlap of stores to memory with other data traffic contributions. So there are some overlaps. This is the best hypothesis that we found for FX700. And here you see, so these components are for different cache levels. And so you can also predict what would be the contributions for different cache levels. So these are predictions. So when data is in L1, we get 2 cycles per vector length as prediction. So when data is in L2, we get 6 cycles per vector length, and so on. And now we have to compare it with measurement. And you see that this was the best hypothesis, and because of this, you see it fits pretty well with the prediction. So the measurement and prediction fits pretty well. So systematic way of how to find this hypothesis is can be seen in the paper, which I have listed below. And it's not just sufficient that it works for one kernel. So here's stream triad, but it has to work for all the kernels. So we have to do a validation test. So once we get a hypothesis, we test it with different kernels to see if it makes sense, this hypothesis. And yeah, so for the here you see the validation for the best hypothesis that fits for the A64FX CPU. And here you see that validation. So the orange bars are for the ECM prediction, and the blue ones are the measurements for in-memory data set. So this is all single core stuff. And note that the y-axis is the runtime, so lower is better. And you see that in most cases that we have an error less than 15 or 10%. So while doing measurements on FX700 or A64FX, we have to take care of there are some things that we have to take care. So one important thing is the data alignment. So normally for typical modern processors, the penalty due to data unalignment was not that big. But for FX700, you see that when the data comes from, especially from main memory, if it's not aligned properly, you might get some penalty. So the blue line is the one with proper alignment, and the black one is the one with 16 bytes alignment. So we just used malloc basically for the black line. So you see that if you need to get the best performance, we need to align data to at least 32 bytes. So this is one important thing that we have to take care. And another important thing is unrolling. So on the left, you see a figure of stencil 2D 5 point. So these are runtime measurements. So these are measurements. So on the y-axis, you have runtime. And the black line is actually the default version which a compiler would produce. So basically, the GCC compiler produced the black line. However, this you see is not optimal. So it's not close to the ECM prediction. So you have to unroll it fairly well so that we get close to the ECM prediction. So this is not typical for modern CPUs, but here you see this. This is just because we saw that the latency of the instructions are high, and also because of the small reservation stations we have not so perfect out of order execution. Therefore, we have to help this out of order execution by unrolling. On the right, you see a different phenomenon because stencil code doesn't have any dependencies. But however, on the right, you see the sum reduction, which actually has some dependency. So there is a dependency on the add instruction because you have to update the sum variable before the new value is calculated. So you have a dependency on this add instruction. Therefore, you see if you don't do any modulo variable expansion or unrolling, you hit the add pipeline latency, which is 9 cycles for this machine. So basically, the GCC compiler always gets this black line. So it can't. So it can't do this modulo variable expansion. At least for this machine, it couldn't. And so we had to do it manually using intrinsics. And you see the blue line is basically when we do sufficient unrolling using modulo variable expansion, you see that we get close to ECM prediction. So basically, the compiler could vectorize the code, but the pipelining was not efficient with the GCC compiler. So we had to do this manually using intrinsics. Yeah. So all the stuff which I told you till now is about single core. So, and we have seen here in the sum case, we have also seen in motivation that it didn't saturate the main memory bandwidth. This was just because we used the default GCC compiler version, which didn't do this modulo variable expansion. So now let's see what happens if we do proper modulo variable expansion. So in the figure in the second figure, that is the sum, you see that with proper unrolling or modulo variable expansion, the sum benchmark actually hits the memory bandwidth saturation. So this is a good thing. And also you see that the ECM model prediction, so ECM model predicts that once you get a single core estimate, it predicts that the performance scales linearly until it hits the saturation. And you see that the model is pretty good when you compare it with the measurements. especially when you compare it with the optimal kernel. And also you see when you compare also the model fits when it's other kernels like Triad and also for stencil kernels. So we did for others, but I didn't have place to put that here. Yeah, so now we saw the sum kernel basically can saturate the main memory bandwidth if you do proper modulo variable expansion. So now the question is, in the motivation picture, we also saw that sparse matrix vector couldn't saturate the main memory bandwidth. So let's now find out why it is. So sparse matrix vector is heavily used in linear algebra. So in many applications, in tons of applications. And de facto storage format for sparse matrices on CPUs is the compressed row storage format. Okay, so basically how we do this sparse matrix vector is we go along each row of the matrices one by one, and it does a dot product between that row of the matrix A and a vector X. So we call it this right-hand side vector X. Since the entries of the sparse matrix is not heavily populated, we just need to access the elements corresponding to the non-zero entries of the A vector of the matrix, and that's why we see that we have some indirect accessing to the X vector. Okay, and so it does this multiplication and stores the value into the B vector. So down you see the pseudocode for sparse matrix vector multiplication. And if you insert this code, for example, into a GCC compiler, it produces a decent SVE vectorized code. So you see that it's a straightforward translation of this pseudocode to the assembly. For example, you can see each of the components. Like, so the first instruction is to load an integer element. So it loads the column indices to the Z0 register. And the third instruction is basically what it does is based on this Z0 register, it gathers elements into the X, gathers elements from the X vector. And then you see there's a load for the matrix entry, and the B elements are constant. It doesn't change with the J loop, that is the innermost loop. So it's kept in a register called Z1. And basically on this Z1, we perform FMA, so fused multiply add. The rest are just loop mechanics. And at the end, we see a horizontal add for this on this Z1 register, which adds all the elements in this Z1 register to one scalar element. So if you do the measurements with this code, you see the performance is what we saw in the motivational picture. It doesn't saturate the main memory bandwidth. And this was done for the HPCG matrix with a dimension of 128 cube. The reason for this can be explained with the ECM model. So with ECM model, you see that the FMA instruction has the same dependency like that of the sum, because it updates the Z1 register. And so to calculate the new value of Z1, it requires the old value of Z1. So there is this dependency. However, with sparse matrices, it's not easy to do modulo variable expansion or unrolling within this short inner loop, because this inner loop goes along the number of non-zeros per row, and this is typically short for sparse matrices. So it's typically in the range of 10 to hundreds. So it's really short. So you can't do proper unrolling. And the other fact is that the horizontal add at the end costs about 11.5 cycles, so pretty high. And this together with the fact that the inner loop is short, for example, for HPCG metrics, that it's just 27. So the inner loop is just 27 in length. These three facts, if you take together, you can see with the ECM model, we get a maximum bandwidth of 160 gigabytes per second. So it doesn't saturate 1 CMG. So on one CMG, you should basically, it could basically do 200 gigabytes per second, but we see with ECM model that it can only reach a max of 160 gigabytes per second. So with ECM model also, you could tell, okay, for sparse matrices, which we encounter in daily life, for most of the matrices, you can't saturate the memory bandwidth of this A64FX machine. So we have to change the data storage format. So you can't saturate the bandwidth with the normal compressed row storage format. So we have to change it to some other format. And that's where we use the Celsius Sigma format. So Celsius Sigma format is a vector-friendly, SIMD-friendly data storage format for sparse matrices. And what we do here is, instead of storing the elements of a matrix row by row, it stores the elements of a matrix in a chunk. So the chunk size is determined by this factor C, so this parameter C. And within a chunk, we store the elements in the column major format. So the benefit of this is that this chunk size C is tunable. So you can make this chunk size big enough such that it's a multiple of the SIMD vector length, which is 8 in this case for A64FX. And also you can add some unrolling factor. So let's say unrolling factor of 4 to avoid this pipeline latency of FMA. So basically on A64FX, it should a chunk size of 8 times 4, that is 32, should be good for this machine. And also another added benefit is that it avoids this horizontal add FADV at the end of the inner loop. And also you don't need any masking operation because all the elements in a chunk are full because it's padded. So there is no loss of vector efficiency. So now let's build up an ECM model for Celsius Sigma format with the HPCG matrix. So if we build it, we see that we need almost 20 cycles to load data from L1 to register. And most of this is caused by the gather instruction. So 90% of this 20 cycles is contributed by this gather instruction. Then we have a negligible amount of runtime for store. And then for L2, for loading data from L2, we need another 5 cycles. And then we need, from memory, we get another 3 cycles. So if you put this together with the ECM model, that is the overlap hypothesis, you see that at the end, you would need 28.8 cycles per row, which means it translates directly to 3.4 gigaflops per second, which is equivalent to 22 gigabytes per second. So this is single core performance. So this is the prediction. So for single core, which you see on the left, and on the right, you see the ECM prediction for multicore. You see that ECM model predicts a linear scaling of performance until it hits the memory bandwidth. So now let's see how close is it to the measurement. And you see with the measurements, this ECM prediction and the measurements lie pretty close. And as predicted by the ECM model, now with Celsius Sigma format, we can saturate the main memory bandwidth. So basically, compared to CRS, we boosted the single core performance by a factor of 2.4x, which enabled us to saturate the main memory bandwidth. So now let's see a bigger picture. So this was just for one typical case, so HPCG matrix. So how does it look for other matrices? So here you see a scan of SpMV performance on different matrices, basically from suit sparse matrix collection and some other matrices. And you see, compared to CRS format, Celsius Sigma format has a clear advantage. And It's only the Celsius sigma format that reaches the optimistic roofline performance limit. What's interesting though is that the matrices towards the right, so basically we ordered the matrices according increasing non-zero wise. So left it's smaller matrices, when you go to the right it's bigger matrices, so having more non-zeros. And what you see is matrices towards right, some of the matrices hit the roofline limit. However, there are lots of matrices on the left which deviates from the model. So we were curious to know why it is. And it turns out it's because of the barrier pane. So this CPU, as I told, uses high bandwidth memory. And when it uses high bandwidth memory, this means the compute time gets lower, because for memory bound cores, the bandwidth is what plays a critical role. So the compute time lowers. However, if the barrier time remains the same, the impact of barrier becomes much more high. This could be proven by, so here I just took 3 matrices from this left region, and you see that if you just remove the barrier, obviously the numerics is wrong, you see that it improves the performance considerably. So the impact of barrier is high. The situation will improve if you use hardware barrier, which is available for this A64FX system. However, unfortunately, the mission in Regensburg, due to some incompatibility with the drivers, couldn't use the hardware barrier. So it's worthwhile to check on hardware barriers too. And yeah, you see the optimistic roofline limit, and for the matrices, some matrices, it shoots above the roofline limit. This is just because it's well below 32 megabytes, the cache size, the last level cache size of this machine. Another important fact that we see on A64FX is, this is an interesting phenomenon that we see on A64FX, is that it saturates only at the very end. So it requires almost all the cores to saturate the main memory bandwidth. And due to this, we have some consequences. Like, if suppose, let's assume that we have an hypothetical machine which has 6 processors, and let's assume it saturates well early. So it needs only 3 cores to saturate the main memory bandwidth. And now let's assume that we have load imbalances between the processors. So here in the figure, you see the work for each of the processors differs. So there is load imbalance. So as time progresses, you see that the number of active cores is at least 3 at most of the time. So this is, if we have at least 3 cores, we can saturate the main memory bandwidth. This means we get full bandwidth at most of the time. And so therefore we don't see any impact from load imbalance if there is an early memory bandwidth saturation. However, on FX700, there is a late saturation. So it doesn't saturate, it needs almost all the cores to saturate the main memory bandwidth. So let's assume it needs 5 cores out of 6 to saturate the main memory bandwidth. And if you now look, what happens is, after some time, when load imbalances start, the active cores is less than 5. So here we have only 3 active cores, but we need 5 active cores to saturate the main memory bandwidth. This means we have a reduction in the bandwidth. And due to this reduction in bandwidth, we lose also performance. So late saturation implies that we are more sensitive to load imbalances and irregularities. So this can be shown, for example, if you compare FX700 and Intel Cascade Lake. So FX700 has a late saturation, while Intel Cascade Lake saturates the memory bandwidth with half the number of cores. So here you see the blue lines are the ones where we did load balancing by rows. So we distributed equal number of rows to different threads. And the orange lines are the ones where we did load balancing by non-zero. So we distributed equal number of non-zeros to threads. And you see there is this performance impact if you change the load balancing scheme. So they are so on FX700, you see that they are really sensitive to this load balancing. So what kind of load balancing you use? However, on Intel Cascade Lake, you don't see this impact because it saturates the main memory bandwidth earlier. So let's now compare it with other modern CPUs. So let's compare FX700 performance with other modern CPUs. So here I have one node of Cascade Lake, the Platinum version, and one node of Rome to compare with, AMD Rome. And here in the figure, you see a comparison between AMD Rome, Intel Cascade Lake, and FX700. So the green ones are the performance for, on the top, we see the green ones, which are the performance for AMD Rome, the blue ones for Intel Cascade Lake, and the orange ones are for FX700. What is striking is basically for AMD Rome, for some matrices, they outperform both the other systems by a huge factor. This is just because AMD Rome has a massive last level cache. Almost it has greater than 500 megabytes, so half a gigabyte actually. So this is pretty impressive, and because of this, the matrices actually fit in the cache of AMD Rome. Yeah, and it also has a higher cache bandwidth compared to Intel or FX700. So you see this massive performance improvement for AMD Rome. Also, when you see for Intel, you don't see this impact because the cache sizes are low, so less than 100 megabytes. If you just consider the last level cache. However, the important stuff or most of the applications work at the memory bound region, so the highlighted region where it does not fit in cache anymore. So let's zoom into this region. So if you just look at the memory bound region, you see that FX700 is a clear winner, and all these CPUs actually obey the roofline limit when the data comes from main memory. And what you see is, on an average, we have almost 2x speed up over Rome and 3x speed up over Cascade Lake for FX700. So down the plot shows the speed up, and you see that for the corresponding speed up. So average, we get almost 2x and 3x speed up. And this actually reflects the difference in the main memory bandwidth between these systems. So last but not least, let's compare it with NVIDIA V100 GPUs. And both the systems actually have almost similar bandwidth. And because of this, you see in most of the cases, the FX700 almost reaches the performance of V100. In most of the cases, you see they are fairly really close. However, there are some regions where FX700 performance is not up to the mark as V100. And these are in most cases for irregular matrices. And we have seen that there are some load balancing issues that are remaining. So we just did this load balancing by row and load balancing by non-zero. However, we also saw that if you use like guided strategy for scheduling, it improves the results for FX700. But this is left for future work actually. Also using sector cache, which is available for FX700, so you can tell which all data need to be cached. So you can specify which all data has to be cached. This might also improve the situation of FX700 a little bit. However, the takeaway message is load balancing issues have to be taken serious when it comes to FX700. So to conclude the talk, we saw that ECM model can be constructed and it's useful for FX700. We could come up with a successful ECM performance model. So we also saw that when constructing ECM model, there is a partial overlap in memory hierarchies. This allows for higher single core performance, which allows for bandwidth to saturate. And also we saw in SpMV, we are almost 2 times, or FX700 is 2 times faster than AMD Rome and 3 times faster than Intel Cascade Lake. And the performance when compared with NVIDIA V100 GPU, it's competitive, although in some cases, there is room for improvement when we compare with V100 GPUs. So the lessons learned, yeah, proper single core optimizations are important, especially due to high latency and inefficiencies in out-of-order execution. So open source compilers have had room for improvement. And for SpMV, we were able to saturate bandwidth with Celsius sigma format. So we had to switch from CRS format. And for irregular matrices, load balancing is an important issue. And so we have to take care of this. And finally, the barrier or synchronization cost can be painful if hardware barrier is not used. So we have to be also aware of that. Yeah, I think I didn't bore you. So thank you for listening. And yeah, I'm grateful for the funding we received and also the architectural support that we received. And yeah, that's it from my side. Thank you. And
thank you very much, Christy. We'll be moving on to the Q&A session here.
Yeah.
So use your raised hand or ask question function of participants, and I'll be opening your mic. And I see that we already have a few questions. So Mr. Michele Martone, I'm opening your mic. Go ahead.
Hello?
Hello, yes, we can hear you.
Well, I've been partially answered. My question was, how do you deal with symmetric matrices, or better, which are your plans for dealing with them?
So right now we did with symmetric matrices, we just did as in general matrices. So we didn't do any special handling for symmetric matrices in this case for this for the slides I have shown. So basically you could do some coloring or something like recursive sparse RRZE format or something like that, but we didn't use it, for example, here in this case.
May I? Do you see CellC as the serial format of something like block oriented? So could you imagine such a setting where you have cell C at a lower level or at a block level inside some larger block?
Yeah, for sure.
Decomposition?
Yeah, for sure it can be done. And also I think there was a paper, I think like a couple of months before from NEC where they did this format, like where they combined it with block. So I think it was from NEC Subasa when doing Celsius Sigma for NEC Subasa vector engines, for example. You can do that. Yeah, you can combine actually.
Okay, thanks. I would have another question, but I give maybe the chance to somebody else first.
Okay. Okay, so we'll be moving to Nicolas Renon. I'm opening your mic. Okay, if you can open it on your end. Okay, Nicolas Renon.
Okay, sorry, maybe I've done a mistake. I would like to thanks very much the speaker for the very clear presentation. I have a very short question. Maybe you mentioned that, and I wasn't. I didn't catch it. For the comparison between Rome, Intel, and FX, did you use the same compiler?
Yeah, so no, so FX700, so the Intel and Rome machines were done with the Intel compiler.
Okay.
But the FX700, obviously we can't do with Intel compiler, so we did it with the GCC compiler.
Okay, okay. And so just last one for the comparison with the V100.
Yeah.
So you started with CUDA kernels. You compare CUDA kernels with the compiled version with GCC of your code?
So one thing I have to specify is all the FX700 code was written with intrinsics, because I told you that GCC compiler doesn't do this modulo variable expansion and some performance optimization. So we had to write the FX700 code with intrinsics, so SVE vector intrinsics.
Okay.
And also the CUDA, the CUDA version, for example, so no, we didn't use the CUDA for here because we compared it with the same data storage format, that is the cell C sigma. So with CUDA, you don't have this cell C sigma format. And because of this, we used a library called Ghost to compare it. So this is, yeah, we used Ghost to compare it.
Okay, thank you very much.
Yeah, welcome.
Let me go through the potential questions as well. Okay, Mathieu Lobe. Mathieu, I'm trying to open your mic. Can you do it on your end? Okay, this is not working. Sorry.
It's working now, no?
Okay, yeah, we can hear you. Go ahead.
Okay, I know. So I would like to come back to the beginning of your presentation, where you show the evolution of the bandwidth according to the number of cores.
Yeah.
I'm not sure to understand very well this this figure. I have a question concerning how you populate the NUMA domains.
Okay, yeah. So we used a compact, this one you meant, right? This plot? Yeah. So we use compact pinning. So that means we, when using 2 cores, for example, so we start with 1 core, which is pinned to the first CMG or first NUMA domain. And then the second core is also pinned, when we have 2 cores, we pin the second core also to the same CMG or same. And that's why we see when we go till 12, so 12 means the first CMG is full, or the first NUMA domain is, that's why we see this memory bandwidth saturation within 1 CMG.
Okay, however, but in this case, maybe I didn't catch why then when you populate the second CMG, second NUMA domain, you don't repeat the same pattern.
This is quite interesting, because the thing is, when you go to the second NUMA domain, what happens is there is only one. So if we have 13 cores, so in the 13 core case, 12 of them are on 1 CMG, and the next one is on the next CMG, right? So the next.
Yes.
This means the one with only 1 core on 1 CMG can access actually the full. Can access the full bandwidth of the second CMG actually, while the other one for the first core, it's shared by this 12 threads.
Okay.
This means it's the first one is faster. However, after each of the stream thread benchmark, for example, you have a barrier. Even though it's faster, it has to wait actually till the first CMG is already done.
Okay.
That's the reason why we see this linear scaling.
I see. Okay, I have just another question. Can you clarify what you mean by unrolling in your presentation? Because I know several definitions of unrolling, and I was not sure about what you do exactly here.
So algorithm you meant?
No, unrolling. When you mean unrolling, so later in your presentation.
Okay, yeah. So unrolling, what I meant is, for example, for the stream thread kernel, which we see here, what we do is, let me see. Yeah, okay. So stream thread kernel, instead of just writing AI is equal to BI plus S into CI, we also do the next iteration. For example, AI plus 1 is equal to BI plus 1 plus S into CI plus 1, for example. And if it's that's 2 times unrolling, and for 4 times unrolling, I would unroll it by a factor of 4. But this is done at, I did it using SVE intrinsic. So this is done for unrolling is on top of vectorization. So if I tell 4 times unrolling, it's 8 times unrolled already for the vectorization, because it's 512. And on top of it, I do again a 4 times unrolling.
Okay. Yeah. I see. So it means that your loop will jump every 32 iterations.
Exactly.
Okay.
Exactly.
Thank you. Thank you.
Yeah, welcome.
Okay, I'm opening the mic of Marcus Rump. Mr. Rump, can you hear us? Okay, no answer there. Let me find someone else. Okay, Mr. Guido Giuntoli. You will need to open your mic on your end.
Yes. Hi, how are you? Guido from
Good.
Munich, Huawei Munich Research Center. So thanks for the presentation. Would it be possible to go to the slide 45?
45, let me see.
Yes, for the SLC Sigma format.
Yeah.
Where you explain, yes.
Yeah.
Yeah, so the one question, I have a pair of questions. So first, in the rightmost figure where you represent the matrix, so are you filling with zeros the white squares?
So yeah, we are filling with so within a chunk, we take a chunk, and within a chunk we look what is the longest row, so which has the longest number of non-zeros per row, and we pad all the elements or all the rows in this chunk to the biggest one. That's why we see here white. Yeah. So what you observe.
So when you do the matrix vector multiplication, are you multiply by zeros there in the white places?
Yeah, exactly.
Okay. So then you report, I think in a slide 52, and a speed up of 2.4 in gigaflops.
Yeah.
So I would like to know if this the speed up is counting these zero multiplications, or you are only taking into account the original multiplication or the useful ones, I mean.
So it's just the useful ones. So it's just the useful ones. And the one good thing about the SLC Sigma format is that I didn't tell it because I didn't have time. Actually, you sort the elements within a scope called sigma. That's why we have the second parameter called sigma. So what happens is if you sort it, you can basically, so the efficiency of, so the number of non-zeros that you have to pad it with can be reduced. So basically, you don't need maybe like 1% or 2% of there is only 2% of the overhead by just for just this unuseful computation. But as you said, in this figure, I took only the useful non-zeros. For all the performance, we just take the useful non-zeros, not the padded ones. We don't consider them for the performance. So it's a fair comparison, I would say.
Okay, very clear. Thank you.
Yeah.
We'll now give the mic to, let me see if there's anyone else who wants to ask a question. Nope. Okay, I don't see anyone. I'm going to come back to Mr. Martone. I think you told her that you had another question.
Yes, thanks. I wish to ask, so which is the maximum excess of, let's say, zeros or padding zeros that you can imagine?
Which one? Can you repeat?
Thinking about the format, this is a question related to what Guido just made 1 minute ago. So which is the maximum excess of padding zeros which you would end up inserting? Because these are unuseful computations, right? So if you do them to performance, right?
Yeah, so it depends on the metric. So how much padding you would need. Basically, what we have seen is for most of the matrices which I showed you here, the padding, the percentage of overhead by padding, or the number of elements that are padded was less than 5% to 5% actually. Was it this your question? Hello?
Yes, this was the context. So if a matrix ends up having completely isolated elements, you have a problem with the format, right?
What do you mean by completely isolated elements? I didn't get it actually. So,
do you require, in this slide here, do you require some of these elements to be adjacent somehow? After the sorting, of course.
Yeah, we have this white space is just padded. That's true, but I didn't understand what you mean by independent padding. Yeah, I didn't get. Maybe. So
maybe I think I can reformulate. Or
yeah, maybe yeah.
The point is, if you know the Voodoo, the BCSR research by Richard Voodoo some 15 years ago.
Yeah.
There you also know that the main problem there was that mostly finite element matrices fitted such blocked formats. And I wanted to understand if you have such a problem as well, or actually not, because of the sorting and grouping which eliminates that.
Sorting some helps in this, but you can also come up with a matrix which has every C element, so every C row is like really populated, so full dense, for example. This would make an enormous padding, so you would require to pad it to a dense matrix, but that's like an artificial matrix where you have all the C row which are full, for example. This would be the worst case that we could imagine. But the good thing about this format compared to LPAC is, in LPAC you scan the entire so you pad it to the biggest row of the entire matrix, but here you pad it only, you look within this window of C. So you need only to pad within to the longest row of this C chunk. Okay, so basically LPAC can be said as when C is equal to number of rows, for example. So you can come up with some cases where it's the worst, for example, when you have every C rows, for example, as dense. Yeah, this could make the performance worse. But we haven't seen such matrices in in real application, basically. So yeah, in most cases I noted maybe a 10% overhead due to padding. Does that answer?
Okay, I will move on to a question by Yuichi Asahi. If you can open your mic to ask your question. You need to click on the mic icon.
Oh, yeah. Can you hear me?
Yes, we can. Go ahead.
Oh, yeah. Thank you for your talk. And I'd like to ask you about the load balancing. So if we just use the OpenMP dynamic scheduling, for example, to mitigate the load balancing issue.
This is not a good this is not a good thing if you use dynamic, because first of all it has OpenMP overheads when you use dynamic. So the overhead is bigger than if you use static scheduling. And then the second problem is it's not just one NUMA node that you have. So you have on A64FX you have four CMGs. So these 4 CMGs are 4 NUMA domains. And with dynamic, you don't have any control over which row is going to which NUMA domain. So basically, this NUMA domains problem, like you can't do this even if you do this golden touch policy, for example, when allocating or initializing the metrics, it doesn't work if you do dynamic scheduling, for example. So that would also make it a problem. So overheads and even NUMA domains, since you have more NUMA domains, so here 4, this won't basically be the best option to do.
Is it true even if we just limit the 1 CMG? Because in general, we often prefer to use the 1 CMG and using MPI to parallelize inside a single node.
that's a good strategy. So that's a good strategy. If we use MPI, for example, or if we could do this also with OpenMP. So like recursive nesting with OpenMP, for example. And yeah, in that case, you could do maybe not dynamic, because dynamic in most of the cases would kill the performance because of the overhead. But something like guided strategy would be really helpful for mitigating this load balancing issue.
Oh, so that's a good suggestion. Thanks. And another question about the about the SBE. You said that the GCC doesn't support SBE intrinsic, so you have to use the SBE intrinsic by yourself. Does Fujitsu compiler support some of the SBE functionality? And so, we can use.
So GCC compiler actually supports SVE intrinsic. So I told it supports the SVE intrinsics. The problem is it's not optimal. So it doesn't do some modulo variable expansion or some performance optimization. So it doesn't know about the architecture much. So yeah, we have to know, because this is a new CPU. So maybe the information about the hardware is not complete within this GCC compiler. And so it doesn't do some optimization, but it can produce SVE code. That's fine. So SVE code is fine with GCC compiler. So the problem is when it comes to optimization. So it doesn't do proper optimization.
Okay. So does it mean that in the Fujitsu compiler can generate a little more optimal code?
I don't know. I didn't have any access to Fujitsu compiler, but I think it should be able to, because the hardware is also from Fujitsu. So I believe, or I think it should be able to, but I didn't test it. I didn't have any access to Fujitsu compiler. I would love to, but I don't have access to it.
Okay, thank you.
Yeah, welcome.
Okay, and we'll take one last question. I thought I saw someone. Yep, Mr. Olivier Marsden. Mr. Marsden, your mic is open. Okay, well, if we don't have anything on this end, then I think we'll close the session here. Thank you, everyone, for attending this webinar. I think it's been really interesting. I would like, obviously, to especially extend my thanks to Christian Georg. As I've told before, the entire webinar is being recorded and will be available on our YouTube channels. You will be receiving a link if you want to see something about it later. I'll also discuss with Christy whether he agrees to share the slides for the presentation, in which case we will send everyone the slides. And we will keep you informed of other upcoming ECO webinars, because we strive to maintain an intense webinar activity, so you will be informed about it. Thank you once again to everyone, and I hope you will be joining us in the future. Goodbye, everyone.
Bye-bye.
Bye.